Assalamualaikum. We continue with this session with a new spectroscopy, which is nuclear magnetic resonance. What is mean nucleus? It involves the nucleus of the atom, and magnetic when we put our sample inside a constant magnetic field, and resonance is the spin flip in the nucleus have a different spin. Means spin flip is the terms for resonance in this spectroscopy. And so the principle of this instrument, it need the radio wave frequency, which is the source of energy for this instrument, and this radio frequency wave is a low energy frequency, and when we interact with the molecule, it only can cause the nucleus spin change. And some elements on with the odd numbers of the atomic number, we have this nucleus spin change. And the principle of this, when we say nucleus spin, when the nucleus spin, if we have it owns angular momentum with the level of P. When if we create a little bit a moment magnet, which is with the formula mu is equal to magnetic ratio times with the angular momentum magnet, and this relationship cause the terms of magnetic quantum number, which is the spin if half, and the spin of the nucleus will be negative half. When they have a different, these two type of energy, which of it owns magnetic field created inside the nucleus, when you put into the constant magnetic field from the instrument, what happened? This magnetic moment now become oriented or against the constant B node. So the potential energy of these two different energy, it become one lower and become one higher. The one with the moment magnet half, which mean the spin up, which is direct to the B node, we have a lower energy. This is the formula for the energy. And for the one that have a against or opposite the B node, that we have a higher energy. The difference of these two energy, when we put the delta E between higher and lower, it become the new formula is magnetic ratio times the Planck constant divided by 2 pi times B node. How we can get 2 pi? Because of this one now become plus, so this become 2 this value, and it cut off with the 4, so now it become only 2. So when we convert back, this value is equal to the formula of frequency, and delta is equal to HV. HV can be related to the frequency from the radio wave frequency. And this is the principle of NMR. When we put a sample inside our constant magnetic field, what happened to the spin on nuclei? So now the spin of nuclei, initially without the external magnetic field, it randomly spin. When we put in the constant magnetic field inside the instrument, the spin now become against or fall aligned with the B node. So because of these two different energy, that's why they have a delta E. When how to get the spin flip from this difference energy? So the nucleus have to absorb energy from the radio frequency. So when the delta E is equal to HV, match these two energy. So now they have energy is absorbed, cause the nucleus to spin flip. When the nucleus spin flip, then it's called a resonance. When the resonance happen, then the signal of NMR is given out. Otherwise, if no resonance, so no NMR signal. So because of these two things that are important in NMR, which is delta E need to be equal to HV, then resonance can happen. That's why here it be illustrated like this, whereas when the delta E is equal to HV, which is the nucleus need to absorb certain radio frequency radiation until enough energy is equal to delta E. Now it can have a spin flip. From higher energy is spin flip. So this spin flip called resonance. When the resonance happens, only the signal of NMR is produced. And in the frequency need for resonance is directly proportional to the magnetic field strength, and the most important thing in NMR is about the frequency and also the B node. Frequency is come from where? This one is come from radio wave energy. This one is come from the magnetic field itself inside the instrument. So this is the two main component in NMR. So these two component is directly proportional. We can change whether to constant the B node and change the frequency, or we constant the frequency and change the B node. And NMR spectrometer are referred to as 300 megahertz instrument, 500 megahertz instrument. So for depending on the frequency of radio frequency used for resonance. And this spectrometer use very powerful magnets and create a small but measurable energy difference between two possible spin state. And two main important parameter in the NMR is frequency and also the magnetic field. Okay, this is the example. You have to try to answer this one. When a proton placed in a magnet, constant magnet, try to calculate the frequency that need to be absorbed by the hydrogen nucleus. After given all this formula, you have to put the formula E is equal to HV and convert back HV to the magnetic ratio time Planck constant divided by 2 pi and get the frequency for this answer. Next is the instrumentation part for the NMR, whereas the main component I said just now is the magnetic field and also radio frequency coil. And when the sample is placed in this detector coil, and the sample keep on irradiate by a certain radio frequency, and when the sample absorb enough radio frequency, then they cause a spin flip resonance inside here. Then the signal will go for the transmitter, receiver, and finally to the recorder. And this is the schematic diagram for NMR instrumentation, and the function for each instrumentation part. Magnets, you can see it can the function of magnet is to produce a stable static magnetic field, which is used to generate macroscopic magnetization in NMR samples. Frequency generator creates an alternating current, induced B node, continuous wave or pulse, and transmitter is provide radio frequency pulse to irradiate the sample with the desired pulse length and frequency to the correct phase and power level. Receiver is to detect the NMR signal generated at the probe and amplify the signal to a level suitable for digitization, and detector is to subtract the base frequency to the output frequency. This is the function for each of the instrumentation part in the NMR. And this is how the real instrument looks like, where we can see the big tank here. Inside the big tank, they have a radio frequency coil, your sample coil, and also the magnetic bar inside here. So here the sample will be dissolved in a solvent. The deuterated solvent will be used for the NMR sample to be dissolved. Why we use deuterated sample? Because we want to avoid the signal from hydrogen. If we use hydrogen, the signal is disturbed by the hydrogen from the solvent. And probes is keep on rotating here and in the magnetic field and irradiate with a short path of different radio frequency. This you can read details here how it can be function of how it had been running the sample inside this instrument. Next, how the signal can be differentiated, because different protons or carbon have different environment. So by the different electronic environments of the proton, you produce a different NMR signal, or this NMR signal is known as a chemical shift. Just now I say only nuclei that have a spin number, which is an odd mass number only, we give signal to the NMR. Otherwise, if a even number such as carbon 12 or proton 2, they have a no signal for the NMR. That's why if you can see, the most common signal for the NMR is this one, H1, we call as proton signal, and C13, which is carbon 13. These two is the common signal for NMR, because in organic compounds there's a lot of interaction between carbon and hydrogen. And this is the criteria need for the magnet, which is if a different magnet, they provide a different magnetic field, and the most common use is superconducting solenoid, which provide high magnetic field, and the material inside is niobium thin wire. And advantage of this superconducting solenoid, it will improve field strength, sensitivity, and when the more sensitive, the signal is more easier to be interpreted. And the things that I say just now, the NMR signal is also known as a chemical shift. Chemical shift of different protons are different. It depends how the environments of the protons in the molecules. And what is chemical shift? Chemical shift is the reference frequency between certain proton with the frequency of the instrument used. So, and the reference for the reference chemical shift is the TMS, which always TMS is equal to 0. If TMS is 1, so it become here, but TMS always 0. Here, the TMS is always 0. The reference value for TMS is 0, and other methyl triplet is relative to TMS, this one, so relative to TMS. And the one value you can see the scale of NMR spectrum is 0 is from the right side, and the bigger number is on the left side. And this side is called a upfield, and this side we call downfield, compared to other spectroscopy, where's the lowest number here and followed to the higher number on the right side. So that's the difference between spectrum of NMR with other chromatogram or spectroscopy data. And this value is called chemical shift, and the symbol is sigma, and the unit is part per million. If you can see, part per million. Just now I say chemical shift is the frequency of your substance divided by operating frequency of spectrometer. Frequency of spectrometer, let's say, is 300 megahertz, and your reference the compound is 300. So now the unit, because of the comparison between frequency of spectrometer, now the chemical shift, the unit of chemical shift become part per million, because time to the power 10 to the power of 6. This is the symbol for chemical shift, that is sigma. And how we can differentiate the position of signal in NMR? As I mentioned, it is affected by the nature of the compounds itself, whether it attached to the saturated compound or it is unsaturated compound, or attached to the electronegative atom. That's affect the signal of the proton. So when the value is bigger, it means it's less shielded. Why the compounds is known as less shield? I gave you an example. Less shielded means the nucleus is less of the electron around the nucleus. So means there are no electron is less, so it can absorb or can feel the magnetic field more. So when it can feel magnetic more, experience the magnetic field very strange. So because of directly proportional between magnetic field and frequency, so they need to absorb higher frequency to get the resonance. That's why when the deshielded compounds, it will have a fall in the downfield, which is the higher number of chemical shift. And when this is an example for the C double bond C, proton that attach to the C double bond C, or proton that attach near to the electronegative atom, we consider as a deshielded proton. So all these shielded proton will fall in the downfield region. And when we see when the atom or nucleus is full of electron, what happen? This one, they feel a less of B node, experience less of B node. And because of the less experience of B node, so this nucleus just need to absorb a little of the frequency from radio wave to get the resonance. That's why it fall in arc field, or this called as the shielded, means saturated nucleus. It always will be in the arc field region, which is a lower number of chemical sheet. We can see these two illustrate the differences between shielded and de-shielded proton. This is the main point, when the shielded proton, what it means shielded, means saturated proton that attach to the saturated carbon, and electron shield the nucleus. Means when saturated compounds, saturated nucleus, they have a lot of electron around it. So that's why the nucleus cannot feel the B node. When the nucleus less feel the B node, so only few energy is need to be absorbed. That's why the frequency is fall in the small value, and this small value is in the arc field region. And the de-shielded means the compounds with the electronegative atom or attached to the C double bond C. The proton is attached to the C double bond C, C triple bond C, or it attached to the electronegative atoms, means it less of the electron around the nucleus, and this will experience a lot of magnetic field from the B node. And when it feel a lot of magnetic field, it need the higher energy to be resonance. That's why it fall in downfield. The value of the chemical shift will keep on increasing. And this again illustrate the same principle like I explained just now. You can read in details for this slide, same as I explained from the previous slide. Position of the signal, whether it's shielded or de-shielded. And this is how we can determine the position of the signal. If we can see, this is one environment, this is the next environment. There are two different environments. This one is labeled as HA, this one is HB. If you can see, this HA is all saturated and DHB is near to the electronegative atom. Which one between this H will fall in the downfield and which one is upfield? If you can see, this one is attached to the electronegative atom. Now this proton become de-shielded, so it fall in the downfield. This one is upfield. You can see read here. Same goes to this one. This proton is attached to the bromine, this proton is attached to the fluorine. Which one is more electronegative? Fluorine is more electronegative, so HB will fall to the downfield compared to the HA. And for these cases, which one is a more electronegative? This one, because two chlorine atom, this one only one, so this one is more downfield compared to HA. That's the position of signal in NMR can be differentiated. And this value is fixed for all the CH. We can see CH3, CH2, CH, the value is fixed. You need to refer in this table will be provided. When we can see the proton attached to the more double bond, it become more higher number. When it become attached to the electronegative atom also, it become more downfield region. And this is a high de-shielded, as I mentioned just now, double bond, de-shielded, and C triple bond C is considered as a shielded because it is, this one is saturated of the electron here, so it become shielded. And next important terms in NMR is spin-spin splitting. In NMR, the signal is not a single peak, but we can see here it looks like double. So this one is considered one signal but have a splitting. It can be split into two, but only we read one signal. Here is one signal only here, but they have a split into triplet. How it can happen like this? Because in NMR they have a spin-spin splitting, mean this signal is affected by the neighboring proton from here. Let's say this one proton is 1, so it can cause, and the rules for the spin-spin splitting is n plus 1. When n plus 1 is H is 1 for the neighboring here, so signal for this one, this H2 is n plus 1, means 1 plus 1 is doublet. So the signal for this one is doublet, and the signal for this one is n plus 1 is 2 plus 1 is triplet. So one signal is doublet, one signal is triplet. That's how spin-spin splitting affected by the neighboring proton. Or if you can read here, it occurs between non-equivalent proton because of just adjacent carbon. In an easy way, I want you to understand the spin-spin splitting in NMR is caused by neighboring proton. Let's consider the example here. And when we see here is a proton for, let's say I'm labeled HA, this one is proton for HB. For signal for HB, is splitting pattern become triplet because the rules of n plus 1. You should written down in your notes that the rules of spin-spin splitting is n plus 1 rules. So to determine this one, the neighboring proton is 1, so the signal for this one is 1 plus 1. This one is doublet, this one is triplet. So the principle here, it says that why it can cause doublet, why it can cause triplet. You can see in details here because when placed in magnetic field B node, CHBr2 can be aligned or against. That's why they have a two spin up and down. So absorbing CH2 feel two slightly different magnetic field, and one slightly larger than B node and one slightly smaller. Since absorbing protons feel two different magnetic field, they absorb two different frequency, this splitting a single absorption into doublet. And this one, the frequency difference measured in hertz because of the coupling constant between these two. They have a constant value. We can draw this one. We cannot simply one is high, one is low. We have, and the distance here between the two peaks is constant, and this one is a J value, and this J value just know, but actually we can calculate, but in this level I don't think so. Just understand what is the coupling constant. So when they have one neighboring proton, they will contribute to the two splitting, and when they have a neighboring proton 2, they will contribute to the 3 splitting pattern. And let us consider, for example, here let's say I'm labeling this one. They show us why the signal of this H is a triplet. They want to explain this, all these notes want to explain why this signal become triplet, because neighboring proton from the adjacent carbon is 2. So when the 2 proton, they have a absorbing protons that feel different magnetic field, one slightly larger, one slightly smaller, and one same strength. That's why they have a triplet. And because of the middle splitting here, it become, the ratio is 1 to 1. That's why we draw the peak is in triplet. One is short, and this one is double, and this one is become 1 back because of this ratio. And spin-spin splitting, how the triplet arise against, it explains us because one proton, one neighboring proton will split into 2, and if we have 3, when we have 2 adjacent proton, we have a triplet because of this ratio 1 to 1. And let's note these rules. Bear in mind, these rules is applied to determine how many the spin-spin splitting of the certain peak, n plus 1. Let's say I want to determine the splitting pattern for this one is considered the same carbon, so no splitting, only neighboring carbon. So this is no neighboring, this one same, this one H and B is considered as neighboring. this carbon is never. This one is considered same, so it's not contribute to the spin-spin splitting. No spin-spin splitting of the same carbon, only the adjacent carbon. Use the rules n+1. Okay, let's see this one, this example. Let's say for this label HA, is it any proton around the neighboring carbon? Neighboring carbon only on the left and right side. More than that, it cannot contribute to the spin-spin splitting. For this HA, only carbon here, no. So this one become no adjacent proton around the carbon. So means this one become a singlet. HA is singlet. HB, this proton neighbor carbon, adjacent carbon is have 3. So use the rules n+1. So this signal HB become quartet. And so no splitting between HA and HB. HB should have a splitting because they have this one. Some mistakes here. Only HA no splitting. And for this one, HA no, HB have why? Because HB have a neighboring proton here. So the peak for the splitting pattern, if 1 we call a singlet, for doublet is 2 is doublet, 3 is triplet, 4 is quartet, 5 is quintet, 6 is sextet, 7 is septet, and more than 7 we consider as multiplet. And this house I showed for you just now how we can identify the splitting pattern. Let's say you want to see the splitting pattern for this signal, so we need to see the neighboring proton here. How much neighboring proton here? HB is 1, so use the rules n+1. So the signal splitting pattern for HA is n+1. 1 plus 1 is 2, so HA is doublet. For HB also is doublet. Use because the neighboring proton is 1. So use the rules of n+1. And for this case, for signal for HA, how we can know? We can see the neighboring proton is 2. So use the rule 2 plus 1 for the signal HA is triplet. 2 plus 1 is 3. So HA signal is triplet. And for HB, we must see the neighboring proton. We cannot see itself proton. If we want to determine, we have to see the neighboring proton. So for this signal HB, the neighboring proton is 1, so 1 plus 1 is doublet. For this one is triplet, for this one also triplet. Use the rules of n+1. This one is 2 plus 1, 2 plus 1, so it become triplet. And for this signal, how I can know is quartet, because 3 plus 1 it become quartet for HA, and for HB splitting pattern is triplet. Because if you want to determine the splitting pattern was for a signal here, we have to see the neighboring proton. We cannot see itself proton. So bear in mind, for splitting pattern, always refer to the neighboring proton, which is right hand side only, not more than that. If I have a different neighboring proton more here, so we cannot see. We only can see right or left. For this signal is quartet, for this signal is doublet, because the use the rules of n+1. So this is the splitting pattern for these cases. So HA signal, we have to see the neighboring proton. From the right side only 1, so the signal for HA is doublet. Why doublet? Because n+1 is only n is 1. So for the signal HB, how we can see? I say just now on the right and the left. So 3 plus 3 is 6, 6 plus 1 is 7. So the peak it should be 7. We can see 1, 2, 3, 4, 5, 6, 7. So this is the splitting pattern for HB. For HA, again, this one is 1 proton. So this one is similar, means they have a 1 signal only HA. And this is again the example for splitting pattern. You can try, which is I just show you HA. How we can determine the HA? Is it any neighboring proton outside? No, because no neighboring proton. Now the signal become singlet. For HB, HC, and HD, because a double bond, all the environment consider a different environment. HB, the signal is come from